Welcome to The Sleepless Universe. In this video, we'll take a calm journey into one of the most intriguing ideas in science and philosophy, the simulation hypothesis. From ancient questions about reality to modern scientific clues, we'll explore what it might mean if our world is an artificial creation. As always, let me know in the comments where you're watching from and what time it is for you. If you enjoy this kind of content, I'd be grateful for a like and a subscribe. And now, I wish you much relaxation and enjoyment as you listen. Setting the stage. Imagine you are lying under a vast night sky, the kind of darkness that only exists far from cities, where the Milky Way stretches like a luminous river across the heavens. The quiet hum of the world fades, replaced by the subtle crackle of your own thoughts. You gaze upward, and it hits you. Everything you see, the stars, the galaxies, even your own body, might not be what you think it is. It might be nothing more than a construct, a grand illusion generated by something or someone far beyond your comprehension. This is not a scene from a science fiction movie. It is a genuine scientific and philosophical possibility. The idea that our universe could be a simulation has slowly moved from fringe speculation to a topic of serious discussion in physics, computer science, and philosophy. The journey we are about to embark on is not one of urgency or anxiety. It is a slow drift through a landscape of ideas, a quiet walk through the corridors of human curiosity. We will take our time, letting each possibility unfold like the pages of an old book. The goal here is not to arrive at a definite answer, because there may never be one, but to explore the depths of the question itself. What if the universe is just a simulation? To begin, we must first understand what is meant by a simulation in this context. When we hear the word, our minds might immediately go to video games, virtual reality headsets, or sophisticated computer programs. These are all forms of simulations, artificial environments created by code and rendered into a sensory experience for an observer. In those cases, the world exists only within the hardware and software that run it. If the power goes out, the simulation ends. If the code is altered, the world changes instantly. Now imagine taking that idea and scaling it up, not just to cover a single environment or scenario, but to encompass everything you have ever known: your home, the Earth, the sun, the billions of galaxies beyond, every photon of light, every particle of matter, every law of physics itself, could be part of an incomprehensibly vast computational construct. This is the core of the simulation hypothesis, that our reality, with all its complexity and apparent solidity, might be nothing more than data running on some unfathomable substrate. The concept is both mind-bending and oddly familiar. In some ways, it echoes ancient philosophical traditions. Plato's allegory of the cave suggested that the world we see is but a shadow of the true reality, a projection on the walls of our perception. In Hindu philosophy, the concept of Maya describes the material world as an illusion, a veil that hides the ultimate truth of existence. Even in Buddhism, the impermanence and constructed nature of reality have been central themes for over 2,000 years. The simulation hypothesis, then, is a modern expression of an ancient suspicion that things are not as they appear. But unlike those earlier ideas, the simulation hypothesis comes with a twist. It's anchored not in mysticism, but in the language of technology. It emerged not from spiritual teachings, but from the rise of computers, digital models, and the dawning awareness of how astonishingly realistic virtual environments can be. This technological lens changes the way we think about the problem. If reality can be simulated on a small scale by humans, perhaps it can be simulated on a universal scale by something else. The question then becomes, who or what would run such a simulation? Here the mind is free to wander. One possibility is that an advanced civilization, millions or even billions of years ahead of us, has the capacity to simulate entire universes for research, entertainment, or reasons we cannot fathom. Another is that the simulators are not biological at all, but artificial intelligences that evolve beyond their creators, now running countless simulations as part of their own purposes. If we are in such a simulation, we face another puzzle. Do the simulators know we exist as conscious beings, or are we simply byproducts of the code? In a video game, Characters can appear to have agency, to make choices, to respond dynamically to the world around them. But in truth, they are driven entirely by lines of code. Yet here we are, asking questions, seeking meaning, and reflecting on our own existence. Could all of that somehow be a product of computation? This line of thought leads to a profound realization. If the simulation is sophisticated enough, there is no clear way to tell the difference between simulated reality and base reality. Our senses are our only tools for interacting with the world, and they can be fooled. Every sight, sound, touch, taste, and smell is nothing more than electrical signals interpreted by the brain. Change those signals and you change reality. In a perfectly designed simulation, there would be no glitch, no flicker, no evidence at all that it was artificial. It would be seamless. It would feel just like this. Of course, such speculation invites skepticism. It feels strange to suggest that everything, our families, our histories, our planet, might be unreal in a physical sense. But is real even a meaningful concept if our only experience of it is mediated through perception? If you dream of standing on a beach, hearing the waves, and feeling the sand beneath your feet, the experience feels real while you are in it. Only when you wake do you recognize it as a dream. The unsettling question is, what if we never wake up? The tone of this conversation can easily slide into the unsettling, but that is not our aim here. Instead, let us treat it as an intellectual adventure, a gentle drift across the boundary between what we know and what we can only imagine. The simulation hypothesis is not a claim that we are in a simulation, but rather a question of whether we could be, and what it would mean if we were. From here, our journey will lead us into history, exploring how the idea emerged and evolved, and why certain discoveries in modern science have breathed new life into it. But before we dive into the specifics, pause for a moment and let the thought settle. The universe you think you know might be something entirely different, a vast, beautiful illusion constructed not by nature, but by design. If this idea sounds like the plot of a science fiction novel, that's because it has been a recurring theme in human storytelling for decades, if not centuries. Films like The Matrix, Tron, and Inception have explored worlds that are indistinguishable from reality, yet entirely artificial. These fictional portrayals serve as cultural touchstones, giving us a language to discuss concepts that otherwise feel too abstract to grasp. But while Hollywood dramatizes the idea, the serious discussion among scientists and philosophers is far more nuanced. One reason the simulation hypothesis has gained traction is the exponential progress in computing power. In just a few decades, we have gone from computers filling entire rooms to devices that fit in our pockets, capable of rendering photorealistic graphics in real time. Video games today simulate worlds of staggering detail, populated by characters whose behaviors are increasingly lifelike. Virtual reality headsets can place us in environments so immersive that, for a brief moment, the brain forgets they are artificial. If this is what humans can accomplish in such a short time, it raises the question, what could a civilization with millions of years of technological advancement achieve? Another driving factor is the rise of artificial intelligence. Modern AI can generate realistic human voices, create lifelike images of people who never existed, and even hold conversations that feel natural. Combine this with advances in physics simulations, which model the behavior of particles and forces with incredible accuracy, and the boundaries between the digital and the physical begin to blur. Theoretically, a sufficiently advanced AI could oversee an entire simulated universe, ensuring every event unfolds according to the laws of that simulated physics. But there's a subtle point here. If the simulation is perfect, it would not just mimic the large-scale structures of the universe, the galaxies, planets, and stars, but also the tiniest quantum fluctuations. This means that the simulation's code would have to operate at a resolution beyond anything we could detect. From our perspective inside the simulation, everything would appear consistent and natural. In fact, the very laws of physics we observe might be nothing more than the rules of the program. This thought can be both humbling and liberating. Humbling because it suggests we might be far from the ultimate level of reality. Liberating because it challenges our assumptions and invites us to think in entirely new ways. If we are in a simulation, what does that mean for free will? Do we make our own choices, or are we executing pre-written lines of code? Or perhaps, just as AI in our world can be given the ability to learn and adapt, we too have been granted a form of emergent consciousness, something that even the simulators might not fully control. Of course, the very act of asking these questions is fascinating in itself. If we are simulated, then our curiosity about the nature of reality is also part of the simulation. Could it be that the purpose of our existence, if there is one, is to eventually discover that we are simulated? Or is that curiosity merely a side effect of the kind of complex intelligence the simulation was designed to foster? Here's another layer. What if simulations can be nested? If our universe is a simulation, then it's conceivable that the universe running ours could also be a simulation within yet another universe. This stack of realities could be infinite, with no ultimate base reality at all. In such a scenario, the question of whether we are simulated becomes less about if, and more about how deep we are in the chain. This leads to a curious paradox. If simulations can be simulated within simulations, then simulated beings could one day create their own simulated universes. In other words, even if we are not at the top level, we could still be creators ourselves. The line between the simulated and the simulator becomes blurred, much like the boundary between player and character in a game. Now, before we move on, let's ground ourselves again. This series is meant to be a calm, deliberate journey. We're not here to provoke existential dread, but to explore the wonder of possibilities. The simulation hypothesis is not a grim pronouncement. It is an invitation to think more deeply about the universe and our place within it. It doesn't tell us what to believe, but it does expand the range of what we can imagine. As we close this first chapter, picture once more that vast night sky. The stars shimmer, the darkness hums with quiet mystery, and somewhere, perhaps beyond the reach of our senses, there could be a place where the code that underlies it all is running. Whether or not we are in a simulation, the questions it raises are worth contemplating. They stretch the mind, they enrich our sense of wonder, and they remind us that the universe, whatever it truly is, still holds secrets far beyond our grasp. In the next chapter, we will step back in time and explore where this idea began, tracing its roots from ancient philosophy to cutting-edge science. The simulation hypothesis may feel like a product of modern technology, but its philosophical ancestors have been with us for millennia, quietly shaping the way we question the nature of reality. Origins of the simulation hypothesis. To truly understand the simulation hypothesis, we must travel far beyond the realms of modern physics and digital technology. The idea that reality might not be what it appears did not begin with computers, nor with science fiction. It has been whispered through the corridors of philosophy, religion, and human imagination for thousands of years. In many ways, our modern notion of a simulated universe is simply a contemporary retelling of an ancient story, a story of illusion, perception, and the search for truth. Our journey begins in the ancient world, where philosophers and spiritual teachers pondered the strange gap between what we experience and what may actually exist. One of the earliest and most famous explorations of this theme can be found in the works of Plato. In his allegory of the cave, Plato described prisoners chained in such a way that they could only see the wall before them. Behind them burned a fire, and between the fire and the prisoners, other people carried objects that cast shadows on the wall. For the prisoners, these shadows were reality itself. They had never seen anything else. But if one prisoner broke free and stepped outside the cave, he would be overwhelmed to discover a world of sunlight, color, and three-dimensional form. The allegory is a reminder that our perception might be limited, that what we take as reality could be nothing more than shadows. In many respects, the allegory of the cave is an early articulation of what the simulation hypothesis would later suggest, that there may be a truer, deeper reality beyond the one we perceive. Plato's insight, though grounded in metaphysics rather than technology, offers a timeless warning that our senses are not the ultimate judges of truth. While ancient Greek philosophy is one root of this idea, another lies in the spiritual traditions of India. Hindu philosophy speaks of Maya, the cosmic illusion that veils the ultimate truth of the universe. According to this worldview, the physical world, with all its forms and phenomena, is not the final reality. It is a projection, a temporary manifestation of something eternal and infinite. Similarly, in certain strands of Buddhism, the nature of existence is seen as impermanent, conditional, and without inherent self. What we cling to as real is in constant flux, and liberation comes from seeing beyond this constructed illusion. These ancient philosophies may not have spoken of processors or code, but they shared a deep intuition that the world might be more like a dream or a mirage than a solid, unchanging thing. The difference is that modern discussions of the simulation hypothesis couch this intuition in the language of information theory and computation, while ancient traditions expressed it through poetry, myth, and spiritual metaphor. Fast forward many centuries, and we encounter the rise of early modern philosophy in Europe. In the 17th century, René Descartes famously undertook a radical project of doubt. He questioned everything he believed to be true, stripping away each layer of certainty until he arrived at one statement he felt could not be doubted. Cogito, ergo sum. I think, therefore I am. In this process, Descartes imagined the possibility of a malicious demon that could be deceiving him about the existence of the external world. Every sight, sound, and sensation might be artificially generated by this deceiver, leaving him trapped in a false reality. While Descartes' demon was not a computer, it served the same role as a simulation in our modern thought experiments, a mechanism for fabricating an entire perceived universe. A few centuries later, in the early 20th century, philosophy began to intersect with the emerging fields of science and logic. Figures like Bertrand Russell and Alfred North Whitehead explored the idea that our understanding of the world is mediated by abstract systems, mathematics, language, and symbolic representation. The notion that the universe itself could be a kind of mathematical structure was beginning to take shape. Then came the mid to late 20th century, and with it, the dawn of the digital era. Computers introduced a new metaphor for reality, the idea of a world generated by code. Suddenly, simulations were not just abstract concepts, they could be experienced directly. Engineers could program models of weather systems, physics experiments, and even simple games where players interacted with a digital world. As computing power grew, so too did the scope and realism of these simulations. This technological leap gave ancient philosophical questions a new framework. If humans could create small-scale simulations, why couldn't a more advanced intelligence create a large-scale one? By the 1970s and 80s, science fiction writers began weaving these themes into their narratives with striking clarity. Stories like Philip K. Dick's Ubik and A Scanner Darkly, or the 1981 film Tron, presented characters trapped in realities they could not fully trust. These works didn't just entertain, they primed the cultural imagination for the possibility that we ourselves could be inside something similar. But it was not until 2003 that the simulation hypothesis took on its most rigorous and widely discussed modern form. That year, philosopher Nick Bostrom published a paper titled, "Are You Living in a Computer Simulation?" In it, he laid out a logical argument known as the simulation argument that forced people to take the idea seriously. Bostrom suggested that one of the following must be true. Civilizations never reach a technological level where they can run realistic ancestor simulations. Civilizations that reach that level choose not to run such simulations. We are almost certainly living in a simulation right now. The power of Bostrom's argument lies in its statistical reasoning. If it is possible to create simulations indistinguishable from reality, and if advanced civilizations choose to run them, even just a fraction of the time, then simulated beings would vastly outnumber beings in base reality. From a probability standpoint, it would be far more likely for you to be one of the simulated beings than one of the rare, real ones. Bostrom's paper did something remarkable. It reframed an age-old question in terms that scientists, philosophers, and technologists could debate without immediately dismissing it as mystical or purely speculative. It shifted the conversation from, "Isn't this just science fiction?" to, "Given what we know about technology and probability, what are the odds this is true?" His argument rippled through academia, tech culture, and popular media. Physicists began to consider whether there might be experimental ways to detect glitches in the fabric of reality. tiny inconsistencies that could reveal the limitations of the simulation's hardware. Philosophers revisited ancient thought experiments, seeing them in a new digital light, and futurists speculated about what a post-human civilization might do with such power. Part of why Bostrom's argument resonated so strongly was the world in which it emerged. By the early 2000s, humanity had already begun living in a blended space between physical and digital realities. The internet was connecting billions of people. Online worlds like Second Life and early massively multiplayer games were showing that humans could spend significant portions of their lives in spaces that existed only in code. The leap from, "I spend time in a simulated space," to, "my entire existence might be simulated," didn't feel quite as far-fetched anymore. Still, the simulation hypothesis didn't exist in isolation. It built upon a lineage of thinkers who had all wrestled with the fragility of perception. Whether it was Plato's shadows, Hindu Maya, Descartes' demon, or the speculative universes of science fiction, the common thread was a profound humility about our ability to know what reality truly is. The modern form of the hypothesis simply gave us a technological metaphor powerful enough to unite these threads into one coherent conversation. Yet even as this idea entered mainstream awareness, it carried with it a subtle irony. If we are in a simulation, then the entire history of the simulation hypothesis, every philosopher, every cultural story, every scientific paper, is also part of the simulation's code. Our act of wondering whether we are simulated could itself be an intended feature, a kind of built-in curiosity. Another fascinating element is how the hypothesis resonates with both materialist and spiritual worldviews, albeit in different ways. To a strict materialist, the simulation is a literal machine, an advanced computational system running the code of our universe. To someone with a more spiritual perspective, the simulation might be seen as a metaphor for divine creation or cosmic design, where the programmer is not an alien civilization, but a higher consciousness. This flexibility in interpretation is one reason the idea has found such wide appeal. By the late 2010s and into the 2020s, the simulation hypothesis had moved from niche philosophy journals into the mouths of tech billionaires and public intellectuals. Elon Musk famously said that the odds we are in base reality are 1 in billions. Neil deGrasse Tyson entertained the idea on stage at science festivals. Even physicists who doubted the hypothesis admitted it was a thought experiment worth taking seriously, if only because it sharpened our thinking about what we mean by real. Looking back, it becomes clear that the simulation hypothesis is not a sudden, radical leap in human thought, but rather the latest chapter in a story we've been telling ourselves for millennia. From ancient caves to virtual reality headsets, from spiritual illusions to computer models, humans have always wrestled with the possibility that there's more to reality than meets the eye. And so, as we close this chapter, we find ourselves standing at an intersection of history. The path behind us is long, winding through philosophy, religion, science, and fiction. The path ahead is uncertain, disappearing into the horizon of what technology, mathematics, and imagination might yet reveal. In the next chapter, we will zoom in on one of the most intriguing intersections between science and the simulation hypothesis, the strange, counterintuitive world of quantum mechanics. From particles that exist in multiple states at once to the mysterious role of the observer, quantum physics has given us phenomena that some see as possible clues that our universe operates more like a programmed simulation than a solid, continuous reality. Whether or not those clues hold up to scrutiny, they offer some of the most fascinating material in this entire discussion. Quantum oddities, clues from the smallest scales. If the simulation hypothesis is true, then somewhere deep within the workings of the universe, there might be subtle traces of its artificial nature, tiny imperfections or patterns in the code of reality. For many thinkers, the most promising place to look for such traces is not in the vastness of galaxies or the slow dance of cosmic structures, but in the realm of the incredibly small, the quantum world. Quantum mechanics is one of the most successful theories in all of science. It governs the behavior of the tiniest particles we know, electrons, photons, quarks, and it has been tested in experiments with astonishing precision. Yet, despite its success, it remains profoundly strange. almost unsettling, because it describes a reality that refuses to behave in the neat, predictable way we expect from our everyday experience. One of the most famous features of quantum mechanics is the principle of superposition. In the quantum world, particles can exist in multiple states at once until they are observed. A single electron can behave as though it is in two different places at the same time. A photon of light can pass through two slits simultaneously, interfering with itself, as though it were a wave spread out across space. Only when we make a measurement does the particle choose one outcome, collapsing into a definite state. This is already counterintuitive enough, but it becomes even stranger when we consider the role of the observer. In the famous double-slit experiment, when particles are not observed, they create an interference pattern, a hallmark of wave-like behavior. But when a measuring device is set up to detect which slit the particle passes through, the interference pattern disappears, and the particle behaves like a solid object going through one path or the other. Somehow, the very act of observation changes the outcome. For some, this peculiar sensitivity to observation hints at something deeper, perhaps even the possibility that the universe behaves differently when watched, much like a rendering engine in a computer game that only generates high-resolution detail when the player looks in a certain direction. In modern gaming, this is called lazy rendering or on-demand rendering, and it's an efficient way to save processing power. The simulation only computes the parts of the world that are relevant to the player at a given moment. Could the quantum collapse be something similar, with reality rendering itself only when necessary? Physicists tend to be cautious about such analogies because quantum mechanics works perfectly well without invoking a simulation. The standard interpretation, known as the Copenhagen interpretation, attributes the strange behavior to the mathematical structure of quantum theory itself without suggesting any underlying code. But the parallel is hard to ignore, especially for those already inclined to think in terms of computation. Another quantum oddity is entanglement, which Albert Einstein once called spooky action at a distance. When two particles become entangled, their properties are linked in such a way that measuring one instantly affects the other, no matter how far apart they are. You could separate two entangled photons by the width of a galaxy, and a change in one would still be reflected in the other instantly. This seems to violate the cosmic speed limit set by the speed of light. And while the effect cannot be used to transmit information faster than light, it still suggests a kind of hidden connectedness in the fabric of reality. In the context of the simulation hypothesis, some have speculated that entanglement could be a sign of an underlying system that is not bound by our physical limitations. In computer science, when two entities share the same source of data, their states can remain synchronized no matter how far apart they are in the simulated environment. The distance is irrelevant because the true connection exists outside the simulated space, in the underlying hardware or program. Then there's the idea of quantization itself. In the physical world as we experience it, space and time seem continuous. You can always imagine moving halfway between 2 points, and then halfway again, and so on without end. But in quantum theory, many properties come in discrete packets, quanta, rather than smooth continua. Light, for example, is made of photons, indivisible packets of energy. If space or time itself turned out to be quantized at the smallest scales, it would be like discovering that the universe runs on pixels with a fundamental resolution beyond which it cannot be divided. Some physicists have even suggested that the search for this fundamental resolution, perhaps at the Planck scale, could be a way of detecting whether the universe is a simulation. If space-time has a smallest possible unit, it might act like the pixels of a cosmic display, revealing the granularity of the simulation's code. This is, of course, speculative, but it shows how quantum phenomena naturally lead some minds toward computational analogies. The mathematical beauty of quantum mechanics also invites comparison to programming. The theory is governed by elegant equations that describe probabilities, transformations, and states with extraordinary precision. In many ways, these equations function like the rules of a game engine, defining the allowable behaviors of the system without needing to hard code every possible outcome. If the universe is a simulation, quantum mechanics could be the physics engine that keeps everything consistent. And yet, it's worth remembering that the quantum world is not only strange, it's deeply real in its consequences. Quantum mechanics makes possible the technologies we rely on every day, from semiconductors to lasers to the GPS systems that guide our travel. If it is part of a simulation, then it is a remarkably consistent and reliable one, robust enough to support a universe of astonishing complexity. If the strangeness of quantum mechanics hints at anything, it is that reality might operate under rules very different from what our intuition expects. And if those rules are encoded, the quantum world could be where the code is most visible, hidden in plain sight, buried in the smallest measurable events. One idea that fascinates both scientists and proponents of the simulation hypothesis is the measurement problem. Why does observation cause a quantum system to collapse into a definite state? If we take the simulation analogy seriously, measurement might be like triggering an event in a computer program, forcing the system to calculate and lock in a specific outcome from a set of probabilities. The randomness we observe could be the result of the simulation's random number generator, ensuring that events remain unpredictable from within. The quantum realm also introduces the possibility of limits to information. In quantum computing, information is stored in qubits, which can hold superpositions of states, allowing immense processing power. If our universe is a simulation, perhaps reality itself is processed in a similar way, with universal qubits defining every particle, force, and field. The processing limitations of the system could manifest as constraints in the physical laws we observe, just as a video game might limit draw distances or frame rates to maintain performance. This leads to an even bolder thought. What if some of the constants of nature, the speed of light, the Planck constant, the gravitational constant, are not fundamental features of reality, but rather parameters chosen by the simulator? In a computer model, these constants could be set arbitrarily to achieve a desired outcome. Perhaps they are fine-tuned not for life in a cosmic sense, but for stability in the simulation's processing. Another intriguing connection between quantum physics and the simulation hypothesis lies in the concept of wave function collapse and its relationship to consciousness. Some interpretations, like the von Neumann-Wigner interpretation, suggest that consciousness plays a role in determining physical reality. If that's the case, then consciousness might be part of the simulation's interface, an active participant in generating the reality we experience. This would blur the lines between observer and observed, making us not just passive inhabitants, but co-creators within the system. There's also the question of quantum fluctuations, tiny, random changes in energy that occur even in the vacuum of space. In standard physics, these fluctuations are a consequence of the uncertainty principle. In a simulation, they could be the equivalent of background noise in the system, unavoidable artifacts of the processing environment. If so, studying these fluctuations might one day reveal the texture of the underlying computation. Skeptics, of course, caution against reading too much into these analogies. Quantum mechanics is strange enough without layering speculative metaphors on top of it. The fact that we can describe some of its behaviors in terms of computing does not necessarily mean the universe is literally a computer program. The resemblance could be coincidental, an artifact of our tendency to interpret unknown phenomena through the lens of our current technology. A few centuries ago, people described the brain as a clockwork mechanism. Today, we call it a biological computer. Both metaphors are shaped by the tools and machines we know best. Yet, even if the parallels are just metaphors, they can be useful. They provide new ways to think about the quantum world, new questions to ask, and new experiments to design. And if one of those experiments ever did reveal evidence of computational structure, such as a limit to space-time resolution, or an identifiable pattern in quantum randomness, it would shake our understanding of reality to its core. The implications of such a discovery would be staggering. It would suggest that everything, every star, every galaxy, every human life is part of an elaborate design. It would mean that the deepest truths about our existence are not found in the visible world, but in the invisible architecture that runs beneath it. We would be living not in a universe of pure chance and physical necessity, but in one shaped by choice, choices made by entities we might never meet, but whose influence is everywhere. As we leave the quantum realm behind, we carry with us the awareness that the smallest scales of nature may hold the most profound mysteries. Whether or not those mysteries are evidence of a simulation, They remind us that reality is far more intricate than it appears. Like the flicker of a pixel or the whisper of a hidden algorithm, the quantum world invites us to look closer, to ask deeper questions, and to consider possibilities we might once have dismissed as fantasy. In the next chapter, we will step away from particles and probabilities to explore a different clue: the role of mathematics in reality. Why does the universe follow mathematical laws with such precision? Is mathematics a human invention that happens to work? Or is it the very language in which the code of the universe is written? If reality is a simulation, then perhaps mathematics is the source code, and by studying it, we might learn something about the mind of the programmer. The role of mathematics in reality. There is something quietly astonishing about the way the universe behaves. The planets orbit their stars according to precise equations. Light bends around massive objects exactly as Einstein's formulas predict. Subatomic particles interact in ways that match the predictions of quantum mechanics down to more decimal places than most people could imagine. Everywhere we look, nature seems to obey mathematical laws. To a casual observer, this might seem unremarkable. Of course, the universe has rules, but the deeper you think about it, the stranger it becomes. Why should reality be structured in such a way that it can be described by mathematics at all? Why should numbers and symbols on a page, human inventions after all, align so perfectly with the behavior of galaxies, oceans, and atoms? This puzzle is sometimes called the unreasonable effectiveness of mathematics, a phrase popularized by physicist Eugene Wigner. He marveled at how abstract mathematical concepts, created without any particular application in mind, often turn out to describe real-world phenomena with uncanny precision. For example, the equations that describe waves in water also describe light, sound, and even the behavior of quantum particles. It's as if mathematics is not just a tool for understanding the universe, but the very fabric from which the universe is made. If we think about the simulation hypothesis, this alignment between math and reality takes on a new light. In a computer simulation, the world is not built from wood, stone, and air. It is built from code. That code is mathematical at its core, defining every interaction, every property, every law of the simulated environment. When we, as simulated beings, study our world and uncover mathematical laws, we may be, in a sense, reverse engineering the source code of the simulation. Consider the way video game worlds are constructed. The graphics you see on the screen, the forests, mountains, and skies, are the result of algorithms and mathematical models. The behavior of characters, the physics of falling objects, even the way light scatters through virtual fog, all of it is generated by math. If a player within that world could perform experiments, they might discover patterns and laws that mirror the algorithms running behind the scenes. In this way, our discovery of physical laws could be evidence of the universe's underlying computational nature. The universality of mathematics is particularly striking when we realize that the same equations can describe wildly different systems. The mathematics of chaos theory, for example, applies to weather patterns, stock market fluctuations, and the population dynamics of animal species. Fractals, those intricate repeating shapes, emerge in everything from the branching of trees to the formation of galaxies. This suggests that the rules of our universe are not arbitrary. They are elegant, efficient, and deeply interconnected. From a simulation perspective, such efficiency makes perfect sense. In programming, reusing the same algorithms for multiple purposes is a sign of elegant design. Instead of writing separate code for every possible situation, a good programmer uses general principles that can generate many different outcomes. If our universe is a simulation, its programmer might have done the same, crafting mathematical rules that apply across scales and contexts, from the quantum realm to the cosmic. One of the most compelling aspects of this idea is the fine-tuning of physical constants, the gravitational constant, the speed of light, the strength of the electromagnetic force. These values seem to be precisely calibrated to allow the existence of complex structures like stars, planets, and life. Change any of them by even a small fraction, and the universe as we know it would be impossible. From the perspective of traditional physics, this fine-tuning is a profound mystery. From the perspective of the simulation hypothesis, It could simply be a matter of choosing parameters in the simulation settings. Of course, this raises its own questions. If the constants are adjustable, who or what set them? Was the choice deliberate, aimed at producing a universe with certain features? Or was it random, with our existence being a fortunate accident in a sea of simulated universes? In programming, running multiple simulations with slightly different parameters is a common way to test outcomes. Could it be that our universe is just one of countless others, each with its own mathematical settings, running in parallel for reasons we can only guess? Another dimension to this puzzle is the question of whether mathematics is discovered or invented. If it is invented, then it is a product of the human mind, and its alignment with reality is a staggering coincidence. If it is discovered, then it exists independently of us, woven into the fabric of reality itself. In the simulation analogy, mathematics would be the source code, the foundational structure that existed before any simulated beings emerged to study it. This idea resonates with the concept of a mathematical universe, proposed by physicist Max Tegmark. He suggests that the universe is not just described by mathematics, it is mathematics. Every particle, force, and field is part of a vast, self-consistent mathematical structure. If this is true, then the simulation hypothesis becomes less a speculative theory and more a statement about the nature of existence. Whether we call it a simulation or a mathematical universe, the underlying reality is the same. The elegance of mathematics also hints at something like intentionality. It's one thing for the universe to follow rules. It's another for those rules to be so beautiful, so symmetrical, so efficient. Symmetry, in particular, plays a central role in physics, governing the conservation of energy, momentum, and charge. Beauty in mathematics is often associated with simplicity and depth, the same qualities that programmers strive for in well-written code. Could the beauty we see in the laws of nature be a reflection of the aesthetic preferences of the programmer? If the elegance of mathematical laws hints at design, then their universality hints at efficiency. This efficiency is not only evident in the way the same formulas apply across scales, but also in the fact that many laws can be expressed in extremely compact form. Einstein's famous E equals mc squared contains in just 5 characters a relationship that unites mass, energy, and the speed of light. Concepts that, before the 20th century, were thought to be entirely separate. Such compression of complexity into simplicity is exactly what one might expect if the universe were built from a carefully written set of instructions. In computing, efficiency is not just a matter of elegance, it's a necessity. Every simulation has limits on memory, processing speed, and storage. To keep a vast, complex system running smoothly, programmers often rely on concise algorithms that produce maximum effect with minimal computational cost. If our universe is a simulation, then its reliance on elegant general mathematical laws could be a way of achieving enormous complexity without overloading the hardware of reality. We can also consider the curious role of mathematics in prediction. Once we uncover a mathematical law, we can use it to predict events that have never been observed. Newton's laws of motion allowed astronomers to predict the existence of Neptune before it was ever seen. Maxwell's equations predicted the existence of radio waves, leading to the development of modern communication. In a simulation, this predictive power might simply reflect our growing familiarity with the rules of the code. As we learn the logic of the system, we can anticipate its outputs with increasing accuracy. Another intriguing aspect is the presence of mathematical structures in areas where we might not expect them. The Fibonacci sequence appears in the spirals of sunflowers, pine cones, and galaxies. The same ratios that determine the pleasing proportions of a rectangle show up in art, architecture, and the branching of trees. These patterns are not enforced by any central planner, at least not in the traditional sense, but emerge naturally from the mathematical rules governing growth and form. In a simulation, such recurring structures might arise from the repeated application of the same generative algorithms, producing similar forms in contexts that seem unrelated. Some mathematicians and philosophers have suggested that the mathematical language of the universe might be the most fundamental reality of all, that everything else is an expression of it. If this is true, then the simulation hypothesis becomes almost inevitable. A mathematical universe is, in essence, a set of rules and relationships. And that is precisely what a simulation is. The difference between a mathematical universe and a simulated one might simply be a matter of perspective. Of course, there are those who caution against jumping to conclusions. The fact that mathematics works so well could be a result of evolutionary necessity. After all, we evolved to perceive and understand patterns that were useful for survival. Our brains might be naturally tuned to notice mathematical order in the world, because it helped our ancestors navigate it. In this view, mathematics is not the code of the universe, but a mental tool that happens to align with reality, because it has been shaped by that reality. Yet, even if this is the case, the alignment remains remarkable. It suggests that the universe has a deep, inherent structure, one that our minds, by whatever means, have managed to grasp. Whether that structure is the product of a cosmic programmer or an impersonal mathematical inevitability, it points to a reality that is far from random. Another angle worth exploring is the possibility that mathematics is not only descriptive, but prescriptive. In our world, the rules of a simulation determine what can and cannot happen. If our universe's mathematics is prescriptive, then the laws of nature are not just summaries of observed patterns. They are the actual constraints that reality must obey. This would mean that nothing in the universe happens without being permitted by the underlying equations. If we entertain this view, then studying mathematics is more than just understanding the universe. It is exploring the very boundaries of what is possible. For scientists, this means that the search for new physical laws is also a search for new regions of the mathematical landscape. For philosophers, it raises the question of whether the mathematical structure of the universe is fixed or could be altered, whether the program could be rewritten. In the simulation hypothesis, this possibility becomes even more tantalizing. If reality is code, and if we could somehow access and modify that code, we might be able to change the laws of physics themselves. While this idea currently belongs to the realm of science fiction, it is no stranger to speculative thinkers. The notion of hacking the universe appears in countless fictional worlds. But if our reality is genuinely simulated, then in principle, such an act could be possible, though it would require access to levels of reality we cannot yet imagine. For now, our best tool remains the quiet, patient study of mathematics itself. Every equation, every proof, every discovery might bring us a step closer to understanding not only how the universe works, but what the universe is. Whether that understanding leads us to a grand designer, an infinite mathematical reality, or simply a deeper appreciation of nature's elegance, the journey is one of profound beauty and endless curiosity. As we leave this chapter, picture the universe not as a random scattering of matter, but as a vast, unfolding expression of mathematical truth. Every falling leaf, every orbiting moon, every pulse of light is part of a grand equation, one that may have been written long before the first stars ignited, and which continues to run, flawlessly, moment by moment. In the next chapter, we will move from the abstract clarity of mathematics to the realm of thought experiments, exploring how philosophers have tested the boundaries of reality itself, with imaginative scenarios that challenge our deepest assumptions. Philosophical thought experiments. Before the simulation hypothesis became a modern scientific talking point, long before computers and quantum mechanics were even imaginable, philosophers had already been exploring ideas that challenged the very nature of reality. They did not have processors or code to reference, but they had an equally powerful tool: the human mind. Through thought experiments, they were able to strip away assumptions, question the reliability of the senses, and imagine scenarios in which reality was far different from how it appeared. Thought experiments are mental laboratories, places where we can bend the rules of the world without the constraints of physical experiments. In them, philosophers can ask, "What if?" without worrying about what is possible in practice. Many of these scenarios bear a striking resemblance to the core questions behind the simulation hypothesis. If reality can be imagined as an illusion in the mind, it's not a huge leap to imagine it as an illusion in the machine. One of the oldest and most famous of these is Plato's allegory of the cave, which we touched upon in an earlier chapter. While often interpreted as a metaphor for education and enlightenment, it also functions as a stark reminder of how limited our perception might be. If we spend our entire lives looking at shadows on a wall, how could we possibly know that there's a whole other reality beyond the cave. Fast forward more than 2,000 years, and we encounter René Descartes' evil demon thought experiment. In his Meditations on First Philosophy, 1641, Descartes imagines that an extremely powerful and malicious being is deliberately deceiving him, feeding false perceptions into his mind so that everything he experiences is an illusion. The demon could make him believe that the sky is blue, that he has hands, that he is sitting by the fire, all while none of it is actually true. Descartes used this scenario not to assert that such a demon exists, but to demonstrate how radically our sense of certainty could be undermined. The evil demon is, in many ways, an early conceptual cousin of the simulation hypothesis. Replace the demon with a supercomputer and the deception with programmed sensory data, and you have a remarkably similar setup. A being living inside a completely fabricated reality, unable to tell the difference. In the 20th century, philosopher Hilary Putnam introduced a similar idea in his brain in a vat scenario. Imagine, he suggested, that your brain has been removed from your body and placed in a tank of life-sustaining fluid. Electrodes connected to it feed it electrical impulses identical to those it would receive if it were still inside a living body. As far as the brain knows, it's still walking through parks, talking to friends, and feeling the warmth of sunlight. But all of those sensations are artificially generated. From the brain's perspective, the simulated world is indistinguishable from the real one. These thought experiments are unsettling because they reveal how fragile our link to reality truly is. Everything we experience is mediated through our senses, and those senses are ultimately just electrical signals interpreted by the brain. If those signals can be faked, then so can the reality they construct. This is precisely the vulnerability that the simulation hypothesis exploits in its modern form. Other philosophical scenarios play with the boundaries of time and causality in ways that echo simulation-like possibilities. The dream argument, which appears in various forms in Eastern and Western philosophy, asks, how can we be certain that our waking life is not itself a dream? The Chinese philosopher Zhuangzi famously wrote of a dream in which he was a butterfly, and upon waking, wondered whether he was a man who had dreamed of being a butterfly, or a butterfly dreaming of being a man. In a simulation context, the question becomes, are we base reality beings who occasionally simulate other worlds, or simulated beings living entirely within a constructed dream? In more recent philosophy, the experience machine proposed by Robert Nozick takes a different angle. He asked, if you could plug into a machine that would give you any experience you desired, indistinguishable from reality, would you choose to do it? This question forces us to confront what we value in life. Do we care more about truth or about the quality of our experiences? If we would choose the machine, perhaps we already value simulated pleasure over authentic reality. Another intriguing scenario is the simulation regress problem. If we are in a simulation, what's to stop that simulation from being inside another simulation, and so on, in an infinite chain? Each level would have its own reality, but only the base level would be truly fundamental. The regress problem highlights the difficulty of ever knowing whether we've reached the bottom layer, or whether such a bottom even exists. These philosophical explorations may seem abstract, but they serve a critical function in the discussion of the simulation hypothesis. They remind us that the possibility of living in a false or constructed reality is not a recent invention. It is a question that has haunted human thought for centuries. What computers and modern science have added is not the question itself, but new ways of framing it, new metaphors for understanding it, and perhaps new tools for investigating it. One reason these thought experiments remain so powerful is that they bypass the need for evidence. We don't need to prove the existence of a demon, a vat, or a simulation to see the force of the argument. They simply demonstrate that our senses and perceptions could, in principle, be deceived. Once we accept that possibility, the question becomes not whether deception is possible, but whether it is happening right now. In the context of the simulation hypothesis, thought experiments give us mental footholds. They allow us to imagine the parameters of a simulated reality, to think about how it might be constructed, and to consider the implications of living in one. They also help us confront the unsettling truth that our desire for certainty may never be fulfilled. For example, consider the hidden variables problem in physics, which has parallels in philosophy. In the early 20th century, some scientists argued that the strange behavior of quantum particles might be due to hidden variables, factors we simply hadn't discovered yet. But experiments like those inspired by John Bell's theorem suggest that such variables, if they exist, operate in ways that defy classical logic. Similarly, in a simulated universe, there may be hidden code or layers of reality that we can never access from within. Philosophers have also explored scenarios that question the nature of personal identity in a potentially simulated world. If your consciousness could be copied perfectly into another medium, say a digital system, would that copy still be you? What if the simulation you inhabit is restarted from a saved state every so often, erasing your memory of the previous runs? Would each restart create a new version of you, or would it be a continuation of the same self? Such questions connect directly to debates about free will in a simulated environment. If our choices are determined by code, do we truly have agency, or are we executing pre-written instructions? And if the simulation's code allows for randomness, perhaps through something akin to quantum probability, does that randomness constitute freedom, or just another kind of constraint? One particularly striking thought experiment that mirrors the simulation hypothesis is philosopher Nick Bostrom's ancestor simulation idea, which forms the backbone of his 2003 paper. In it, he asks us to imagine future civilizations with computational power so vast they could simulate the entire history of their species, down to the thoughts and sensations of every individual. If such simulations were possible and common, then statistically, most beings like us would be simulated rather than real. This is not a conclusion drawn from physical evidence, but from probability reasoning, a mental experiment that uses logic to challenge our assumptions. There is also the unsettling Boltzmann brain scenario, named after the physicist Ludwig Boltzmann. In certain interpretations of cosmology, random fluctuations in the universe could, given enough time, produce a fully formed brain, complete with memories and perceptions. Such a brain would believe itself to be living in a coherent reality, but in fact, it would be nothing more than a temporary fluctuation in chaos. In a simulation, the same could be true. Our memories, history, and sense of continuity could be illusions generated moments ago with no past at all. Even more provocatively, some thought experiments explore the idea that the act of contemplating the simulation hypothesis might influence whether we are in one. If simulators are observing us for specific reasons, scientific curiosity, entertainment, or even ethical evaluation, then our awareness of their existence might change how they run the simulation. In some speculative scenarios, merely discussing the possibility could trigger changes in the simulated environment, much like a character in a story suddenly becoming aware they are fictional. Ultimately, philosophical thought experiments serve as reminders that the simulation hypothesis is not just about physics or technology. It is about the limits of human knowledge. They force us to confront the fact that, from within our own reality, there may be no definitive way to prove whether it is real in an absolute sense. And yet, that limitation doesn't diminish the value of the question. Instead, it deepens it. As we close this chapter, imagine standing at the edge of a mirror-lined hallway where every reflection contains another reflection, and the depth seems infinite. Philosophy, in this sense, is not about finding the final mirror. It's about learning to see the infinite reflections for what they are, and to wonder about the space beyond them. In the next chapter, we will turn from the realm of imagination to the realm of possibility, exploring whether the simulation hypothesis is technologically feasible. Could we, or any advanced civilization, actually build a simulation detailed enough to fool its inhabitants into believing it is reality? To answer that, we'll need to consider the limits of computing power, the speed of technological progress, and the surprising ways in which the line between simulated and physical worlds is already beginning to blur. Technological feasibility. The simulation hypothesis is captivating as a thought experiment, but it becomes even more intriguing and controversial when we ask whether it could actually be done. Is it technologically possible to simulate a universe like ours in such detail that its inhabitants would have no idea they were simulated? Could we, or some other advanced civilization, have the computational resources to make that happen? To begin answering that question, we have to understand the scale of the challenge. Our universe contains roughly 2 trillion galaxies, each with hundreds of billions of stars, and around many of those stars are planets, moons, and countless other celestial bodies. If we tried to simulate every atom in just a single planet, the amount of data would be staggering. And if we extended that to the entire observable universe, the numbers become almost inconceivably large, far beyond the capabilities of our current computers. At first glance, that seems like a fatal blow to the idea. If simulating every particle in the universe is impossible for us, why would it be possible for anyone else, even an advanced civilization? But here's where things get interesting. You might not need to simulate the entire universe at once. In many modern computer games, the environment is not fully rendered in detail until the player looks at it or interacts with it. Areas that are far away from the player's position are represented in a simplified form, with only the most important details calculated. In game development, this technique is called level of detail scaling, or on-demand rendering. The same principle could apply to a simulated universe. The simulation might only generate high-resolution detail where and when it is needed, such as when a conscious observer is looking at it, while leaving the rest in a lower-resolution state. If our universe operates in this way, then vast amounts of computational power could be saved. The deep interiors of stars, for example, might not be fully calculated until someone builds a telescope capable of observing them in detail. Even then, the simulation could calculate just enough to match the expected physics, without simulating every subatomic interaction. This leads us to an important consideration: the resolution of the simulation. In our physical reality, we might assume that space and time are continuous, infinitely divisible. But if they are quantized at a fundamental level, broken into the smallest possible units, such as the Planck length for space and the Planck time for time, then the simulation would have a natural limit to its resolution. This would be like discovering that our universe has pixels. If such granularity exists, simulating the universe becomes more manageable, because there is a smallest scale beyond which no detail needs to be calculated. We can also think about computational shortcuts. In physics, many systems can be described using approximations that are good enough for the scale at which they are being observed. Weather simulations, for example, don't track every single molecule in the atmosphere. They model airflows, temperature changes, and pressure systems at a larger scale. Similarly, a simulated universe might not simulate every interaction in real time. Instead, it could rely on probabilistic rules that generate realistic outcomes without calculating every intermediate step. From a technological standpoint, the key question becomes, how much processing power would it actually take to simulate conscious beings and the world they experience? Surprisingly, the most computationally expensive part of a universe simulation might not be the galaxies or planets, but the minds of its inhabitants. Consciousness is still a mystery to us, and we have no agreed-upon theory of how it emerges from the physical brain. If it can be replicated by simulating the activity of neurons or something analogous, then the amount of computation needed per conscious mind could be enormous. Yet, there is a counterpoint. In our own world, artificial intelligence is advancing rapidly. Neural networks inspired by the brain are already capable of recognizing images, translating languages, and even generating text and art in ways that can feel surprisingly human. These systems do not require simulating every neuron in a human brain. They use far simpler architectures, yet produce results that mimic certain aspects of human thought. If a simulated universe used similar shortcuts, it might be able to simulate consciousness convincingly, without duplicating every biological detail. This raises the possibility that the inhabitants of a simulation might not be conscious in the way we are. They might simply be sophisticated, non-player characters, NPCs, behaving in ways that are indistinguishable from real consciousness to anyone within the simulation. But if the simulation did include genuine consciousness, the computational load would be higher. Whether that is feasible depends on the limits of the underlying hardware. To understand those limits, we need to think about computing on a cosmic scale. Right now, the fastest supercomputers in the world operate at speeds measured in exaflops, quintillions of calculations per second. That is impressive by human standards, but still a tiny fraction of what might be possible for a civilization, millions or billions of years more advanced than ours. If Moore's law or some successor trend continued for even a few more centuries, the gap between our current capabilities and theirs could be unimaginably vast. Moreover, advanced civilizations might not be limited to traditional silicon-based computing. They could use quantum computing, harnessing the superposition of quantum states to perform massive numbers of calculations in parallel. They might even tap into forms of computation we cannot yet imagine, such as manipulating space-time itself to perform calculations, or using the energy of entire stars as processing fuel. From our perspective, such capabilities might seem like science fiction, but so would the smartphones in our pockets to someone living just a few centuries ago. If there are civilizations that have reached such a level, then building a universe-scale simulation might be well within their reach. If such advanced computing power exists, the next question is, why would anyone, or anything, want to use it to simulate a universe like ours? The motives could be as varied as the civilizations themselves. One possibility is scientific research. Just as we run computer models to study climate change or galaxy formation, an advanced civilization might simulate entire universes to test theories about cosmology, physics, or even the evolution of life. In such a scenario, we could be part of an experiment designed to observe how civilizations develop under certain conditions. Another possibility is historical reconstruction. Imagine having the ability to recreate the past in perfect detail, to watch it unfold exactly as it did, or as it might have under slightly different circumstances. An advanced civilization might simulate its own history or the history of other worlds to learn from it or simply to satisfy curiosity. In this case, we might be ancestor simulations, existing only so that our simulators can study the emergence of intelligent life. There's also the possibility of entertainment. To beings with unimaginable lifespans and resources, simulating entire worlds filled with lifelike characters could be a form of art, storytelling, or even gaming. In this view, our universe could be a kind of immersive entertainment platform, an elaborate simulation run for the amusement of its creators. The idea is unsettling, but it mirrors what we already do on a much smaller scale. Millions of people play video games that simulate cities, societies, and even entire galaxies. To the simulated beings in those games, if they could think and feel, it would all seem perfectly real. Of course, even if it is technologically feasible to run such simulations, there would still be practical constraints. One is error management. In complex simulations, errors, what gamers might call bugs or glitches, can occur. If our universe is simulated, then anomalies in physical laws, unexpected cosmic events, or unexplained phenomena could be the result of such glitches. While science usually seeks natural explanations for anomalies, the simulation perspective leaves open the possibility that some might be computational artifacts. Another constraint is storage. Even with incredible processing power, storing the data for every event, particle, and interaction in a universe would be overwhelming. A clever solution would be to avoid storing everything permanently. Instead, the simulation might dynamically generate events as needed, based on probabilistic rules, and only store the state of the universe at certain checkpoints, similar to save points in a game. This would drastically reduce storage requirements while still producing a consistent and believable reality. Interestingly, this approach could also explain why the past sometimes appears uncertain at the smallest scales. In quantum mechanics, until an event is observed or measured, it exists only as a set of probabilities. If the simulation doesn't store every past detail with infinite precision, it could recreate them when needed, filling in the gaps in a way that's consistent with the rules of physics. From our perspective, this would look like quantum uncertainty. From the simulation's perspective, it's just efficient memory management. We can also consider the economics of simulation. Even an advanced civilization with vast resources might choose to optimize its simulations to save energy and processing capacity. They might run many small-scale simulations rather than one massive one, or simulate only the portions of a universe relevant to their goals. This means that, if we are in a simulation, the reality we experience might not extend infinitely in all directions or times. It might be on demand, generated only as far as we can observe. Some theorists suggest that if we look closely enough at the universe, we might find signs of these optimizations. For example, there could be a maximum resolution to reality, a point beyond which space and time cannot be divided. There could be limits on the amount of randomness in quantum events or subtle repeating patterns in physical constants that reveal an underlying algorithm. At the same time, we must acknowledge that proving such limits exist would be extraordinarily difficult from inside the simulation. Our measuring tools are part of the simulation, and the results they produce are constrained by the same rules. If the simulators have designed the system well, there may be no detectable difference between their simulation and a base reality. In that case, the only way we would know for certain is if they chose to reveal themselves, an event that would be as transformative as it is improbable. From a purely technological perspective, the biggest open question is whether consciousness itself can be simulated in full fidelity. If consciousness emerges purely from the processing of information, if it is an emergent property of complex systems, then it is theoretically possible to simulate it, given enough computational power. But if consciousness depends on some property of the physical world that cannot be replicated in the code, then even the most advanced civilization might only be able to create convincing imitations, not genuine conscious beings. This uncertainty echoes one of the most profound challenges of the simulation hypothesis. Even if it is technologically feasible, we may never know whether we are in a simulation, because the simulation could be designed to hide its nature perfectly. The only clues we might have are the ones that slip through accidentally, small inconsistencies, unexplained phenomena, or hints buried in the mathematical structure of reality itself. As we close this chapter, imagine the perspective of the hypothetical simulator. They have the tools to create worlds as rich and complex as ours, the ability to populate them with thinking, feeling beings, and the curiosity to see what unfolds, whether they are scientists, historians, artists, or something beyond our categories entirely. Their creation would be, from our point of view, indistinguishable from reality. And that is perhaps the most humbling part of the technological feasibility question. If it can be done, then from inside, it would feel exactly like this. In the next chapter, we will examine the potential signs and tests of a simulation. If we are indeed living inside a vast computational construct, is there any way to detect it? Could the structure of space-time, the behavior of particles, or the patterns in cosmic radiation reveal the fingerprints of a hidden program? And if such evidence existed, what would it mean for our understanding of reality? Signs and tests of a simulation. If we are living inside a simulation, is there any way to find out? Could the structure of our universe hold clues, subtle fingerprints of an underlying computational framework? This question moves the simulation hypothesis from philosophy into the realm of science, because it invites us to search for empirical evidence. At first glance, the task seems impossible. If the simulation is perfect, we would have no way of distinguishing it from base reality. Our senses, our instruments, even the physical laws we use to analyze data, would all be part of the simulation, bound by its rules. Yet, history has shown that even well-designed systems can sometimes reveal themselves through unexpected glitches, patterns, or constraints. The challenge is to figure out what such signs might look like for a simulated universe. One of the most discussed possibilities is the detection of a smallest possible unit of space or time, a fundamental pixel of reality. If our universe is computed, then it may operate on a discrete grid, much like the pixels in a digital image or the frames in a video. Physicists have long speculated about the Planck length and Planck time as potential fundamental limits. If experiments were to confirm that reality is quantized at this scale, it wouldn't prove the simulation hypothesis, but it would fit naturally with the idea that the universe runs on finite resolution. Another proposed test involves looking for anisotropies, tiny directional differences in the cosmic microwave background, CMB, radiation, the afterglow of the Big Bang. If the universe were simulated on a grid-like computational architecture, its geometry might not be perfectly smooth at the largest scales. Instead, the grid structure could subtly influence the distribution of radiation, creating patterns that wouldn't occur in a truly continuous spacetime. Researchers have actually searched for such anomalies, though so far results have been inconclusive. We can also think about processing constraints. In complex simulations, computational limits sometimes manifest as lag or simplified rendering in less important areas. Applied to the universe, this idea suggests that regions we cannot currently observe might not be fully simulated until we try to observe them. If this were true, then pointing a telescope into previously unobserved space could, in theory, cause the simulation to generate new data on the fly. Of course, the simulation would need to do this seamlessly to avoid detection, but subtle delays or statistical anomalies in newly gathered data could be a potential clue. Quantum mechanics offers another potential testing ground. The seemingly random outcomes of quantum events could be generated by a pseudo-random numbers generator within the simulation. In principle, if this generator had imperfections, patterns might emerge over a large enough dataset, patterns that deviate from true randomness. This would be incredibly difficult to detect, but not impossible in theory. Some have even proposed that cosmic rays, high-energy particles from deep space, could carry signs of a simulated reality. If the simulation uses a finite grid, the highest energy particles might interact differently depending on their direction of travel, revealing the orientation of the underlying lattice. Detecting such directional dependence would require extremely precise measurements, but it is within the reach of future experiments. There is also the possibility of deliberate messages. If a simulation is being run by conscious beings, they might choose to leave clues for its inhabitants, either as a test, a form of communication, or an artistic flourish. Such messages could be hidden in the mathematical constants of nature, in the structure of DNA, or in patterns within the CMB. Some scientists have speculated that pi or other transcendental numbers might contain coded messages if computed to enough digits, though so far, none have been found. Of course, we must also acknowledge that every one of these potential signs could have natural explanations. The danger in searching for evidence of a simulation is that we might misinterpret random noise, experimental errors, or genuine physical phenomena as signs of artificiality. This is why simulation tests must be designed with extraordinary care, using rigorous controls and peer review. One of the more radical suggestions comes from theoretical physics. The idea that certain features of our universe's laws, such as the speed of light limit, might actually be computational constraints. In a networked computer game, there is a maximum rate at which information can travel, determined by processing and communication speeds. In our universe, the speed of light functions as just such a limit. While there are strong physical explanations for this in relativity, the parallel to computational limits is intriguing. Even the apparent fine-tuning of the universe could be viewed as a sign. If the fundamental constants are set with extreme precision to allow life, as many physicists have noted, it might indicate deliberate calibration, like adjusting the parameters of a simulation to achieve a desired outcome. This could be evidence of design, though whether that design is the work of a deity, a natural multiverse process, or an advanced simulator remains an open question. Then there is the question of glitches. In human-made simulations, glitches are usually obvious. Objects passing through walls, characters freezing mid-action. If our universe glitched, would we notice? Perhaps in small ways, such as reports of inexplicable phenomena, memory inconsistencies, or rare events that seem to defy physical laws. Most such claims are better explained by psychology or observational error. But if a genuine glitch ever occurred and could be documented scientifically, it would be a remarkable finding. While glitches in our universe, if they exist, would almost certainly be subtle, there is a fascinating question about whether they might appear more often at the edges of our knowledge, places where the simulation might not be as high resolution because there are fewer observers looking closely. Deep space is one candidate. The microscopic quantum realm is another. It's possible that at these extremes, the simulation could rely on probabilistic shortcuts, creating phenomena that appear strange or even paradoxical when examined. The idea of observer-dependent rendering, which we touched upon earlier, offers a natural explanation for some of the oddities in quantum physics. If the simulation only generates high-resolution detail when observed, then the collapse of the wave function in quantum mechanics could simply be the moment when the simulation computes a specific outcome for the benefit of the observer. In unobserved regions, reality could exist only as a set of probabilities or instructions, waiting to be resolved. This brings us to the notion of testable predictions. If the simulation hypothesis is correct, then it should be possible, at least in principle, to design experiments aimed at detecting the computational limits or shortcuts of our universe. For example, randomness testing. Gathering vast datasets of quantum events and searching for patterns that would be inconsistent with true randomness, perhaps revealing the signature of a pseudo-random number generator. Directional cosmic ray analysis, measuring the energy distribution of cosmic rays to see if they vary depending on direction, which could hint at a grid-like structure of space-time. High-precision timing experiments, detecting tiny delays or inconsistencies in the particle interactions that could indicate processing time or resource allocation by the simulation. Mathematical constant analysis, searching for non-random sequences buried deep within constants like pi, e, or the fine structure constant, which could be intentional markers. The challenge, of course, is that even if such anomalies are found, they would not automatically prove the simulation hypothesis. They might also point to new, unknown aspects of physics. This is why many scientists caution against seeing the simulation idea as a catch-all explanation for mysteries. It risks stopping inquiry rather than deepening it. That said, the search for evidence of a simulation has the potential to push science forward, even if the hypothesis turns out to be wrong. For example, the hunt for quantized spacetime could lead to breakthroughs in quantum gravity theories. Efforts to understand the limits of randomness could sharpen our understanding of quantum mechanics. And even the philosophical implications, questions about observation, reality, and perception, can inspire new approaches to old problems. There's also the intriguing possibility that a simulation might be intentionally undetectable until a certain level of development is reached. Perhaps the simulators have placed unlock conditions on our reality, only revealing themselves or leaving clear signs once we have achieved specific milestones, like a cosmic achievement system in a game. This idea is speculative, but it adds a layer of narrative possibility to the hypothesis. Some thinkers have suggested that if we were to prove we are in a simulation, the simulators might choose to shut it down, modify it, or interact with us directly. In that sense, finding definitive proof might be a double-edged sword. It would be the most profound discovery in human history, but it could also fundamentally change the nature of the simulation, perhaps even ending it. This gives a curious, almost mythological flavor to the search, echoing ancient stories in which mortals seek to meet their gods, not always with happy results. On the other hand, if the simulators wanted us to know, they could make their presence obvious at any moment. A sudden message in the sky, a change in physical constants, or a universal broadcast into every mind would remove all doubt. The fact that this hasn't happened might mean they have no interest in revealing themselves, or it might mean that doing so would interfere with the purpose of the simulation, whatever that purpose may be. In the absence of such overt signs, we are left with the slow, careful work of scientific investigation. The search for simulation evidence requires patience, creativity, and a willingness to accept uncertainty. It also requires humility, because the limits of our perspective from inside the universe may mean that the truth is beyond our reach. As we close this chapter, we can imagine ourselves as characters in a vast, unending detective story. The clues we seek may be hidden in the very equations that govern reality, in the faint hiss of ancient cosmic light, or in the unpredictable flicker of quantum events. We may never find them, or we may stumble upon them tomorrow. But the search itself is part of what makes the question worth asking and the journey worth taking. In the next chapter, we will explore the philosophical and existential consequences of discovering that we live in a simulation. How would it change our sense of meaning, morality, and purpose? Would it diminish our achievements or give them new significance? And perhaps most importantly, would knowing the truth make us any happier? Implications, if true. Imagine for a moment that the simulation hypothesis is no longer a theory, no longer a matter of speculation or late-night philosophical debate. Imagine it has been proven beyond doubt. The data is clear, the evidence irrefutable. We are living inside a simulation. What happens next? The immediate reaction would almost certainly be a mix of awe, disbelief, excitement, and fear. For some, the confirmation might be liberating, a long-awaited answer to one of the deepest questions about existence. For others, it could be deeply unsettling, even destabilizing. After all, if our reality is artificial, what does that mean for our sense of self, our achievements, our relationships, and our future? One of the first questions people would ask is, does it matter? If the simulation is indistinguishable from what we previously thought was reality, does the label simulation change anything about our day-to-day lives? We would still wake up in the morning, eat breakfast, talk to friends, go to work. The sun would still rise, the seasons would still change. In this sense, discovering the simulation might change nothing practical at all, and yet, for many, it would change everything. One of the most profound shifts would be in our understanding of meaning. For centuries, humans have debated whether meaning is something inherent in the universe or something we create for ourselves. If the universe is a simulation, then meaning might be something programmed into it, or perhaps deliberately left open for us to define. For some, this could lead to a sense of existential emptiness. If everything is artificial, does it really matter? But for others, it could inspire a new kind of purpose. If our existence is intentional, then perhaps we are part of a larger story, one whose author we might one day come to understand. Morality would also come under new scrutiny. If our reality is programmed, are our moral instincts just lines of code, or do they reflect something deeper? Perhaps even the values of the simulator. Some might argue that morality becomes meaningless if we are simulated beings, while others might claim the opposite, that morality takes on more meaning because it could be the very reason the simulation exists. If the simulators are observing us, perhaps they are evaluating how we treat each other, testing whether compassion, cooperation, and justice can emerge in a constructed world. Religious and spiritual beliefs would be profoundly affected. Some traditions might embrace the simulation as confirmation of long-held teachings about a creator or higher power. The programmer could be seen as a modern equivalent of God, and the simulation itself as the divine creation. Other belief systems might resist this framing, arguing that the simulators, if they are finite beings, are not truly gods and that ultimate reality lies beyond even their reach. In some ways, the simulation revelation could bridge the gap between science and spirituality, providing a shared language for discussing creation, purpose, and destiny. Science itself would face both challenges and opportunities. On one hand, certain scientific questions might suddenly seem less urgent. If the constants of nature were chosen by the simulators, then their values might not be explainable by natural laws. On the other hand, new scientific fields would emerge, focused on understanding the nature of the simulation, its architecture, and its possible boundaries. Physicists might try to map the hardware on which the simulation runs. Computer scientists might look for ways to interact with or even modify the code. The quest to understand the universe would shift toward the quest to understand the system running it. There would also be social and political consequences. Governments would need to decide how to present and manage this information. Would it be treated as a matter of public knowledge or as a closely guarded secret? If access to the simulation's control panel were possible, who would have the right to use it? The potential for abuse would be enormous. Imagine the power to alter the laws of physics, rewrite history, or control the minds of simulated beings. Even the belief that such control might be possible could destabilize societies, as people question whether events are real or scripted. On a personal level, people's responses would likely fall into a wide spectrum. Some would embrace the idea with curiosity, diving into new philosophical and scientific explorations. Others might retreat into denial, continuing to live as if nothing had changed. A few might reject the simulation outright, insisting that it is impossible to really prove, clinging to the idea that their world is as real as it feels. And then there would be those who see the discovery as an opportunity to live more boldly, treating life as a kind of game or challenge to be explored without fear. Perhaps the most intriguing question would be, can we communicate with the simulators? If they exist, are they aware of us as individuals, or do they see us only as patterns in the data? Would they respond if we tried to send a message? Some might advocate for attempts to contact them, while others would warn against it, fearing interference or even termination of the simulation. The idea that our reality could be shut down or altered beyond recognition would become a genuine concern. There is also the question of nested simulations. If we are in a simulation and we ourselves develop the technology to run our own simulated universes, we could create new layers of reality, each with its own inhabitants unaware of their simulated nature. This could lead to ethical dilemmas. Would we be morally responsible for the well-being of our simulated beings? Would we owe them the truth about their existence? And how would we react if our simulators asked the same of us? If confirmation of the simulation hypothesis became public, it would also reshape art, culture, and human storytelling. Writers, filmmakers, and game designers would be inspired to explore the implications, not just as speculative fiction, but as a reflection of our lived reality. Stories might shift from portraying simulated worlds as mere fantasy to treating them as serious commentary on our actual condition. Music, visual art, and literature could take on new layers of meaning, exploring themes of code, design, and the blurred line between creation and creator. Education would likely evolve as well. Philosophy classes might treat the simulation hypothesis as a core topic, alongside theories of knowledge and reality. Physics courses could incorporate simulations-based interpretations of quantum mechanics and cosmology. Computer science programs might train students not only to design simulations, but to think critically about the ethical and existential consequences of doing so. Over time, a new interdisciplinary field, perhaps called simulology, could emerge, combining philosophy, physics, and computational theory into a single discipline focused on understanding simulated existence. For many individuals, the biggest shift might be psychological. Knowing you are in a simulation could create a sense of detachment from everyday problems. Traffic jams, bills, and petty arguments might seem trivial compared to the vast mystery of the simulation itself. On the other hand, some might experience the opposite reaction, throwing themselves more fully into life, knowing that their time within the simulation is finite and precious. In this way, the revelation could produce both apathy and renewed passion, depending on how each person interprets it. There would also be deep questions about death and what happens afterward. If the mind is a computational process, then perhaps it could be saved, transferred, or even rebooted after physical death. The simulators might keep backups of every conscious being, allowing them to restore us if they chose. This idea could transform humanity's relationship with mortality, offering the possibility of digital immortality, but also raising ethical concerns about consent, autonomy, and the nature of identity. Would a restored version of you truly be you, or just a convincing copy? Some would wonder whether the simulators have already intervened in our world, subtly influencing events or guiding the course of history. Every unexplained leap in human progress, every strange coincidence, could be reinterpreted as a potential sign of their involvement. This could lead to new forms of conspiracy thinking, but also to serious academic study of historical anomalies in search of patterns. Whether those patterns exist would be an open question, but the mere possibility could captivate minds for generations. The economic implications could be equally significant. If reality is a simulation, then in theory, the simulators could adjust its parameters, changing resource availability, weather patterns, or even the laws of supply and demand. While this sounds fantastical, the belief that it might happen could affect markets, as investors and policymakers react to the possibility of outside influence. Insurance companies might even consider simulation risk when designing policies, just as they consider natural disasters today. On a geopolitical level, the revelation could both unite and divide humanity. It might unite us by showing that all humans share the same fundamental situation. We are all inhabitants of the same artificial world, facing the same existential reality. National borders and old rivalries could seem less important compared to our collective position within the simulation. But it could also divide us, as groups form competing interpretations about the nature and intentions of the simulators, leading to new ideological conflicts. There is also the ethical dimension of how we would treat our own simulations, should we continue to build them. Once we know for certain that simulated beings could, in principle, be conscious, the moral responsibility toward our creations would become unavoidable. Laws might be created to protect simulated lives from unnecessary suffering. Entire debates could arise about whether shutting down a simulation is morally equivalent to ending a world. Perhaps the most profound implication, however, is the shift in perspective it would bring about. If we are part of a designed system, then every aspect of our reality, from the laws of physics to the arc of human history, exists for a reason, even if we do not yet know what that reason is. This could instill a sense of cosmic significance, a feeling that our lives matter not just to us, but to the very fabric of the simulation. Or it could lead to the opposite conclusion, that we are nothing more than a temporary curiosity, a passing experiment in a vast digital multiverse. Either way, the certainty that we are in a simulation would transform how we think about ourselves, our place in the universe, and the meaning of existence itself. It would be the most profound paradigm shift in human history, one that no individual, institution, or culture could fully ignore. The simulation would become the backdrop against which all other questions are asked and all other stories are told. As we close this chapter, we are left with a paradox. The simulation hypothesis, if proven true, could simultaneously make the universe feel smaller, bounded by the limits of its code, and infinitely larger by revealing that beyond our reality lies another, and perhaps another beyond that. In the next chapter, we will confront the other side of the debate, the arguments against the simulation hypothesis, and why many scientists and philosophers believe that, no matter how compelling the idea might seem, it is unlikely to be true. Counterarguments and Skepticism. The simulation and hypothesis is seductive. It offers an explanation for the mysteries of the universe, ties together threads from philosophy, physics, and computer science, and invites us to imagine ourselves as part of something vast and intentional. But not everyone is convinced. In fact, many scientists, philosophers, and skeptics believe the idea is either unlikely or fundamentally flawed. Some see it as an intriguing metaphor rather than a literal possibility. Others argue that it's simply unfalsifiable, a question that can never be answered definitively, and therefore not a scientific theory at all. The first major criticism is the problem of testability. For a theory to be scientific, it must be possible to test it in a way that could prove it false. The simulation hypothesis, however, may be immune to such testing. Any evidence we gather is itself part of the simulation. Any measurement we make is mediated by the simulation's rules. If the simulators are sufficiently advanced, they could ensure that no experiment ever reveals their presence. This leads some to dismiss the hypothesis as unfalsifiable speculation. Interesting for discussion, but outside the scope of science. A related objection is the anthropic trap. The idea here is that we may be projecting our own technological culture onto the cosmos. We live in an age of computers, code, and virtual realities. So we imagine the universe in those terms. But just as earlier cultures imagined the universe as a clockwork mechanism or a divine creation, our simulation metaphor may simply reflect the tools and ideas of our own time. 1,000 years from now, if humanity survives, people might have entirely different metaphors for reality, ones that make our simulation models seem quaint. There is also the scale problem. Proponents of the simulation hypothesis sometimes underestimate the sheer computational complexity required to simulate a universe as detailed as ours. Even if we take shortcuts, rendering only what's observed, using probabilistic rules instead of full particle simulations, the amount of processing needed to simulate billions of conscious beings interacting in a consistent physical world could still be astronomically high. Some argue that it may be more difficult to simulate reality than to simply let reality exist, making the whole enterprise inefficient and unlikely. Another criticism focuses on the assumption of motive. The hypothesis often assumes that advanced civilizations would want to run simulations of conscious beings, but we have no evidence for that. They might have ethical objections to creating and potentially harming simulated lives. They might find such projects boring, irrelevant, or wasteful. Or they might have laws or cultural taboos that prevent them from engaging in such experiments. The assumption that they would be interested in running a simulation like ours is, skeptics argue, a projection of human curiosity, not a given. Philosophers also raise the issue of epistemic equivalence. Even if we are in a simulation, the reality we experience is the only one available to us. In practical terms, there is no difference between a simulated universe and a base reality if the rules are consistent and the experience is indistinguishable. From this perspective, the simulation hypothesis doesn't add useful explanatory power. It simply renames our reality without changing its substance. This is similar to the brain in a vat thought experiment. Even if it's true, it doesn't alter our ability to function within our perceived world. Another skeptical stance comes from the complexity of consciousness. We don't yet understand how consciousness arises from physical processes, and it may turn out to be something that cannot be replicated in a purely computational system. If consciousness depends on specific physical phenomena, say quantum processes in the brain, then simulating it might be impossible, no matter how advanced the technology. In that case, the beings in a simulation might be sophisticated imitations, but not genuinely conscious. From a physics standpoint, some scientists argue that there is no evidence for computational limits in the universe. The speed of light, quantum uncertainty, and Planck scale granularity are all explainable within existing physical theories without invoking simulation. While these features may resemble aspects of computing, the resemblance could be purely coincidental. Nature's laws might simply be the way they are, without needing to be programmed by anyone. Finally, there is the possibility of misdirection. Even if anomalies or patterns were discovered in the universe that hinted at artificiality, they might have explanations unrelated to simulation. Unusual cosmic patterns could be the result of unknown natural processes. Apparent randomness in quantum events could be truly random. Fine-tuning of constants could arise from a multiverse, where countless universes with different parameters exist, and we happen to live in one that supports life. These counterarguments don't necessarily disprove the simulation hypothesis. They just highlight that the case for it is far from airtight. For every point in its favor, there is a plausible alternative explanation or a fundamental uncertainty that keeps the question open. Another major line of skepticism comes from the principle of parsimony, also known as Occam's razor. This principle suggests that when two explanations can account for the same observations, the simpler one is usually preferable. In the case of the simulation hypothesis, the simpler explanation might be that the universe simply exists as a natural phenomenon, rather than as the product of an elaborate artificial construct. Adding simulators, computers, and code introduces extra assumptions without providing clear, unique predictions that can be tested. Critics also warn about the danger of anthropocentrism in our reasoning. The idea that we might be the center of attention in a vast cosmic simulation could be seen as a modern echo of outdated beliefs that placed humanity at the center of the universe. History has repeatedly shown that our place in the cosmos is not special in the way we once imagined. Earth is not the center of the solar system. The sun is not the center of the galaxy, and our galaxy is not the center of the universe. In this light, the notion that an advanced civilization is focusing its immense resources on simulating us could be just another form of self-importance. There's also the issue of probabilistic reasoning in Nick Bostrom's original argument. His famous trilemma, either advanced civilizations don't survive long enough to run simulations, they choose not to run them, or we are almost certainly in one, relies on assumptions about the behavior of civilizations we have never observed. Some critics argue that probability estimates in this context are meaningless because they depend on unknown factors such as the distribution of technological capability, the ethics of alien species, and the practical challenges of large-scale simulation. Without real data, these probabilities might be little more than educated guesses. Another concern is the potential unfalsifiability of nested simulations. If our universe is a simulation, then the simulator's universe might also be a simulation, and so on in an infinite regress. In such a scenario, it becomes impossible to say what base reality even means, or whether it exists at all. If every layer of reality could be simulated, then the distinction between real and simulated might lose its meaning entirely. Some philosophers see this as a sign that the hypothesis collapses into incoherence when pushed to its logical extreme. A different kind of counterargument focuses on human psychology. We are storytelling creatures drawn to narratives that give structure and meaning to our experiences. The simulation hypothesis offers a grand, unifying story, that explains the mysteries of the universe while placing us in a role that is both special and mysterious. But this very appeal could be a reason to doubt it. Our attraction to the idea might be driven more by emotional satisfaction than by evidence. Like myths and religions before it, the simulation story could simply be another way for humans to make sense of the unknown. Then there is the continuity of physical law. Throughout history, as our understanding of the universe has expanded, the laws of nature have proven remarkably consistent across scales and contexts. If we were in a simulation, skeptics argue, we might expect to see more irregularities, more places where the code shows through, especially in extreme conditions. But so far, every new experiment, from probing the interior of atoms to observing distant galaxies, has confirmed that the same physical laws apply everywhere. While this doesn't rule out a simulation, it does make it harder to argue that one is evident. Some scientists take a pragmatic stance. Even if the simulation hypothesis were true, it wouldn't change the way we conduct science. Our task would still be to study the universe we can observe, formulate theories, and test them through experiment. Whether those theories describe real particles or simulated ones, the methods and results would remain the same. From this viewpoint, the hypothesis may be intellectually stimulating, but practically irrelevant. Finally, there's a cautionary note about misallocation of resources. If researchers focus too heavily on proving or disproving the simulation hypothesis, they may divert attention from more fruitful scientific work. While the idea can inspire creative thinking, it risks becoming a distraction if pursued at the expense of testable, applicable research in physics, computing, and other fields. In the end, the skeptic's case is not necessarily that the simulation hypothesis is wrong, but that it is unproven, possibly unprovable, and perhaps unnecessary as an explanation for the universe we inhabit. It remains a compelling idea, but one that must be held alongside other possibilities, and examined with the same critical rigor we apply to all scientific and philosophical claims. As we close this chapter, we stand at a balance point. On one side, the simulation hypothesis offers an elegant, unifying way to interpret reality, with tantalizing hints from physics, mathematics, and philosophy. On the other side, the skeptical perspective reminds us of the limits of our knowledge, the dangers of projection, and the need for caution in the face of uncertainty. In the next chapter, we will move toward the conclusion of our journey, reflecting on what we have learned, the mysteries that remain, and the ways we might continue exploring the question, whether or not we ever find the final answer, living in the possible illusion. After a journey through philosophy, quantum physics, mathematics, technology, and skepticism, we arrive at the threshold of our final reflection. The simulation hypothesis has taken us from the shadows of Plato's cave to the smallest particles in the quantum realm, from ancient myths of illusion to modern computer architectures. Along the way, we have asked and re-asked one central question: what if the universe is just a simulation? We have explored reasons why it might be possible, examined the clues some believe point toward it, and considered the motives and capabilities of hypothetical simulators. We have also confronted the counterarguments, the doubts, the cautions, and the philosophical challenges to the hypothesis. And now, standing at the end of this exploration, we face the most personal question of all. How should we live if it might be true? One answer, perhaps the simplest, is exactly as we already do. If the simulation is perfect or nearly so, then our reality is functionally indistinguishable from what we once called base reality. The relationships we build, the goals we pursue, the joys and sorrows we experience, they all remain real to us, regardless of their ultimate substrate. Whether our world runs on atoms or algorithms, the meaning we find in it is no less genuine. But for many, the possibility of a simulated existence is not something they can simply set aside. It lingers in the background, coloring their sense of purpose and their understanding of what life means. If our reality is designed, then perhaps it has a purpose, one chosen by the simulators. That purpose might be entirely beyond our understanding, or it might be simple and universal: to see what intelligent beings will do when given freedom, constraints, and the chance to wonder about their own nature. Living with that possibility can be empowering. It invites us to think of life as an experiment in creativity, morality, and discovery. In a simulation, every choice we make could be part of a data set observed by entities beyond our comprehension. While this idea might feel intrusive to some, others find it motivating, as if they are players in a grand game where every act of kindness, every pursuit of knowledge, every leap of imagination matters in ways we cannot yet see. On the other hand, the notion of being simulated can also provoke existential unease. If our existence depends entirely on the will or whim of the simulators, then we may be more fragile than we ever imagined. A simple decision on their part, perhaps as trivial to them as closing a program on a computer, could end our entire reality. This awareness can lead to feelings of vulnerability, even futility. And yet, it also mirrors the fragility we already live with in what we assume to be base reality. Asteroid impacts, supernovae, pandemics, and countless other forces beyond our control could end our world at any moment. The difference is one of narrative, not of vulnerability. There is also a middle path, to acknowledge the possibility without letting it dominate our thinking. Just as ancient sailors navigated without knowing the full shape of the earth, we can live meaningful lives without knowing the full nature of reality. The simulation hypothesis, in this sense, becomes one more layer in the tapestry of human thought. An idea to ponder, a story to tell, a lens through which to view the mystery of existence. In practical terms, what would change if the hypothesis were proven true? For most people, perhaps very little. We would still need to eat, sleep, work, love, and dream. Our day-to-day challenges would remain. The difference would be in the frame we place around those experiences. Some might see life as a performance for unseen observers. Others might feel liberated to live more boldly, knowing that their actions might echo beyond the boundaries of this simulated world. Still others might find comfort in the idea that death could be just a transition, whether to another simulation, to base reality, or to some state entirely beyond our comprehension. If we take the simulation hypothesis seriously, even without proof, it can inspire a shift in perspective similar to what astronauts describe as the overview effect. The profound sense of interconnectedness and fragility they feel when seeing Earth from space. In our case, it would be the realization that everything we know, every star, every atom, every thought, is part of a vast, possibly intentional construct. That realization could foster a greater sense of unity among people, dissolving some of the divisions that have long defined human history. At the same time, the hypothesis could deepen our curiosity. If our reality is simulated, then what lies beyond it? Is there a base reality where the simulators exist? Could there be multiple layers of simulations, each with its own inhabitants, stretching upward or downward in a chain without end? And if so, might it be possible for us to ascend or descend through those layers, either by technological means or through some kind of intervention from the simulators themselves? We might also consider the ethics of our own technological future. If we reach the point where we can run simulations of conscious beings, our moral responsibilities will be immense. The way we treat our simulated creations could reflect on how our simulators treat us, or serve as the very tests they are running. In this way, the hypothesis could act as a mirror, forcing us to confront the possibility that we are both the simulated and the simulators, shaping and shaped by layers of reality. For individuals, living in light of the simulation hypothesis can mean choosing how to interpret it in a way that enhances, rather than diminishes, life's meaning. Some might choose to see it as evidence of a purposeful universe, with every experience contributing to a larger design. Others might take the opposite approach, embracing the idea that if this is a simulation, then the only meaning is the meaning we create, and therefore, we are free to define it without fear of cosmic judgment. In either case, the hypothesis challenges us to be intentional with our lives. If unseen observers are watching, let them see us at our best, curious, compassionate, and creative. If no one is watching, those qualities still make the simulated world richer and more fulfilling for us and those around us. In that sense, the simulation hypothesis can serve as a kind of moral thought experiment. How would you live if you knew your life was being observed by its creator? And would you live any differently if it wasn't? There is also a strange comfort in knowing that, simulated or not, we are part of something that exists, The substrate may be silicon or it may be space-time, but in both cases, our experiences are real to us. Our emotions are real. Our struggles are real. The stories we tell, the art we make, the love we feel, these are not diminished by the possibility of simulation. If anything, the fact that such richness can exist within an artificial construct is a testament to the power and beauty of creation itself. Perhaps in the end, the simulation hypothesis is less about discovering whether it is true and more about exploring what it means to live as if it might be. It is a reminder that reality, whatever its ultimate nature, is both fragile and astonishing. That we exist at all, whether as lines of code or as arrangements of atoms, remains the greatest mystery of all. So, we return to where we began, lying under a vast night sky, wondering about the nature of everything above and around us. Whether we are gazing into the depths of base reality or the intricately rendered surface of a cosmic simulation, the stars still shine, the air still moves, and life continues to unfold. In that sense, the most important truth is not whether the universe is real, but that it is ours here and now, for as long as it lasts. And so we live, questioning, exploring, creating. Not because we know the answers, but because the questions themselves are worth the journey. I hope you enjoyed this gentle journey through the simulation hypothesis. Whether you find the idea unsettling or inspiring, perhaps it's given you a new way of looking at the world around you. If you're still awake, there's another journey waiting for you here on the screen. Until next time, sleep well and keep wondering.